All right, let's jump right into this. In this explainer, we're dissecting a fascinating yet completely invisible issue that's quietly crippling production-grade AI applications everywhere. We are talking about document redundancy. It's a silent bottleneck that actively breaks the context windows of large language models and completely ruins the user experience in search. So if you've ever wondered why your highly tuned vector database just seems to repeat itself over and over, you are absolutely in the right place. So here is our roadmap for today. We're going to cover the silent ranking bottleneck, the three-stage ranking pipeline, pointwise versus listwise logic, maximal marginal relevance, the VRSD geometric breakthrough, and finally, optimizing LLM context windows. Let's get to it. Section 1. The silent ranking bottleneck. Check out this observation from a developer on Reddit. It hits the nail on the head regarding the harsh reality of moving from a simple tutorial to an actual production environment. When you scale up your document corpus, relying solely on simple cosine similarity often means you're going to retrieve the exact same document, or maybe slightly overlapping slices of it, multiple times. This literally chokes the LLM with duplicate data, and that leaves absolutely zero room in the context window for diverse, complementary information. Think about what that redundancy looks like in practice. Imagine you're building an e-commerce search. A naive vector search for black t-shirt might return 10 identical black t-shirts. I mean, that is extreme homogeneity and, quite frankly, a terrible user experience. On the flip side, a truly diverse result set for something like red tomatoes returns fresh ones, canned ones, organic options, maybe even a tomato salad recipe. It covers the entire semantic space of the user's intent, giving them real choices. Section 2. The three-stage ranking pipeline. Now, modern recommendation and search systems don't just magically happen in one step. They operate in a very specific three-stage pipeline. Stage 1 is retrieval, where we quickly pull a high recall set of thousands of candidates from a massive database. Then we have Stage 2, pointwise scoring. This is where heavy machine learning models assign precise, relevant scores to those candidates. And finally, we hit Stage 3, listwise ordering. This is the absolutely crucial final mile where the homogeneity problem gets solved and where diversity and actual business logic are applied. Let's zoom in on Stage 2 for a second. Pointwise scoring is all about assigning an independent score, like the probability of a click, to individual candidates. We usually use powerful models like cross-encoders for this. Now, don't get me wrong, these models are incredibly smart at identifying if a user will engage with a single item. But here's the catch. They make these predictions in complete isolation. They literally have no idea what else is sitting next to them on the page. Section 3. Pointwise versus listwise logic. So to really understand this, we have to contrast these two core questions. Pointwise logic simply asks, how good is this one item? But listwise logic asks the much more important question, how good is this set of items together? You simply cannot just take a sorted list of top pointwise scores and call it a finished product. If you do, you're going to get those 10 identical black t-shirts. We have to evaluate the list as a cohesive unit. Because if you don't apply this listwise logic, you fall victim to the explore-exploit trade-off. Pure exploitation of known user preferences creates this brutal feedback loop. The user gets stuck in a monotonous filter bubble, seeing only what they've clicked on before. Meanwhile, new items suffer from what we call item starvation and are never shown because they lack historical data. Listwise ordering breaks this loop by intentionally injecting exploration and diversity into the mix. Section 4. Maximal marginal relevance, or MMR. Historically, MMR has been the go-to industry algorithm here. It works by greedily building your final list one item at a time. As it considers a brand new candidate item, it looks at its relevance score, sure, but then it applies a penalty based on how similar that candidate is to the items you've already placed in the result set. It is constantly weighing relevance against novelty. MMR manages this delicate balancing act using a tuning parameter called lambda. If you set lambda to 1, you're prioritizing pure relevance, which drops you right back into extreme homogeneity. If lambda is 0, you tell the system you only care about diversity, which usually results in extreme irrelevance. You're showing things the user didn't even ask for. So the sweet spot is usually a balanced trade-off somewhere between 0.5 and 0.7. But here is the major fatal flaw of MMR. That optimal lambda, it's practically impossible to know ahead of time for every single query because you are tuning a single static parameter across incredibly complex, high-dimensional vector spaces. It causes totally unpredictable optimization fluctuations. Sometimes a lambda of 0.5 works perfectly, but other times it completely breaks the intent of the search. Section 5. The VRSD Geometric Breakthrough. This is where things get really cool. There's a framework called Vector Retrieval with Similarity and Diversity, or VSRD for short. Instead of manually weighing relevance against diversity using that finicky lambda parameter, VSRD actually unifies them. It does this by maximizing the alignment between the original query vector and the literal sum of all the retrieved candidate vectors. To really grasp the geometric intuition behind this, think about vectors approaching the query in space. If we force the combined summed vector to point as closely as possible to the query vector, we naturally force the individual candidate vectors to surround the query from different diverse angles. If they were all clustered tightly together, their sum would just shoot off in one narrow direction. So, by optimizing the sum, we force the vectors to approach the query from diverse complementary facets. It's brilliant. And, this isn't just theory. It's backed up by formal mathematical proofs. Proposition 1 states that in an n-dimensional vector space, the sum of two vectors necessarily lies between them. Because the sum vector physically sits between the candidates, maximizing its similarity to the query inherently means you are pulling candidates that bracket the query from different sides. You achieve strict relevance and multifaceted coverage all at the same time, without tweaking any arbitrary tuning parameters. Okay, there is a tiny catch though. While VRSD perfectly balances our two objectives theoretically, calculating the absolute optimal set of vectors to maximize this sum is what computer scientists call an NP-complete problem. Basically, it's a massive combinatorial optimization nightmare. Since we obviously can't brute force it in real time, engineers rely on highly efficient heuristic algorithms that approximate this sum vector alignment incredibly well at scale. Finally, Section 6. Optimizing LLM context windows. So what does this all mean for us? Well, recent papers have proven that using these diversity-aware selection methods directly enhances retrieval-augmented generation, or RAG. By ensuring multifaceted coverage, we feed the LLM a much richer context. This strategically mitigates the infamous order of n-squared self-attention bottleneck because we just aren't wasting precious tokens on redundant data anymore. It significantly increases the recall of relevant facts and directly prevents the LLM from hallucinating missing information. This actually gives us a crystal-clear diagnostic tool for your own pipeline. If you evaluate your RAG system and see high context precision, meaning the chunks you pulled are very accurate, but you have low context recall, it means your system is missing the bigger picture. You're pulling highly accurate but ultimately incomplete and redundant text chunks. Geometric listwise approaches like VRSD are the exact engineering solution to fix this specific symptom. So, as we wrap up this explainer, I want to leave you with a provocative thought about your own architecture. When your users ask a complex question, is your vector search actually exploring the semantic space to give them a complete, diverse answer? Or is it just blindly repeating itself? Implementing listwise logic isn't just some minor optimization. It's the difference between a frustrating search bar and a truly intelligent system. Thanks for exploring the anatomy of modern ranking with me today.
If you found this helpful, hit subscribe and the bell so you never miss a video.